Okay, so in this first lecture, what I want to do is bring in some of the assumptions that are going to relate to everything that we talk about in this particular course. And the first assumption is that we're dealing with beam structures, okay, fairly straightforward. And what that means essentially in the context of this course is that our structures are going to be subject to some component of loading that is perpendicular to the longitudinal axis of the structure. And this is as opposed to axially loaded members or shafts, for example. But we'll dig into that now in a couple of minutes. The next assumption is that our structures are two-dimensional or they are planar. And in brief, all that means is that our structure, its loading and its response or its deflection can completely be captured in the 2D plane of the page or the screen. So it's not a three-dimensional, although in real life any structure is three-dimensional, but we can represent our structure as a two-dimensional structure in the plane of the page. So all of the relevant information can be captured in that plane of the page or screen. And the third assumption is that our structure is statically determinate. And all that means is that we are able to analyze the structure and determine the magnitudes of the reactions using only the equations of equilibrium, of which there are three for a 2D planar structure. So those are the three assumptions that are going to relate to or apply to everything that we do in this particular course. And we're doing that because it allows us, or we're limiting ourselves with these assumptions because they allow us to capture, or rather to introduce, bending moments and shear forces without having to worry about any other sort of more complicated phenomena going on. So we'll dig a little bit more into each one of these assumptions now over the course of this lecture. So, beam structures. Let's get this clear in our minds. What are we talking about? Well, essentially, what we mean is it means that there's some component of loading. Okay, so some component of loading that is perpendicular to the longitudinal axis of the structure. Okay, so we have a few things going on there. So we're saying a component of loading, first of all. That's the first thing to identify. Then we're saying that we have that component is perpendicular to the longitudinal axis of the structure. So like most things, this becomes a lot more simple, a lot easier if we draw it out. So if we imagine a simple beam structure, okay, so just take it as granted that that is a beam structure. And we have a pin support on the left, we have a roller support on the right. Okay, so far so good. Now, this axis I'm drawing here is the longitudinal axis of the structure. It runs along the structure. Now, what we're saying is there must be, for that to be a beam in the context of our discussion for the purposes of this module, I mean, the word beam can be rather loosely defined, but we want to specifically define a beam for the purposes of this as a structural element that experiences loading or a component of loading perpendicular to this dashed axis I've drawn. So what does it look like? It simply looks like, for example, a load A. Okay, that load is perpendicular because that there is a right angle. So that's perpendicular to the axis of the structure, therefore it is a beam. Now, say for example, we didn't have a nice perpendicular load. Say we had an inclined load. Okay, let's call that the load B. Right, well remember I said a component of loading, and that inclined load B can be represented by a vertical component, which we'll call BV for vertical, and a horizontal component, which I will call BH. Okay, BH. So B, I could get rid of B and replace it with BV and BH, and that would have the exact same effect. Now all of a sudden we notice that we have a component, BV, that is perpendicular to the axis of the structure, the longitudinal axis of the structure. So that is a beam. And it is that loading, that perpendicular loading to the longitudinal axis, which will induce a bending moment and a shear force, which we're subsequently going to go on and look at in more detail. So it's worth pointing out that we are specifying this as a beam as opposed to an axially loaded member. So you might have said, well, surely all sort of structures are beams because they all experience loading. But we also have axially loaded members, which are not beams, okay? So we're going to say, so not let's imagine I'm going to draw the structure with some thickness now. Just, let me see, we've got a longitudinal axis along the structure like so. Now, if that structure experienced a load like this, okay, an axial compression is what we would call this. Okay, so that's an axially loaded member. All right, which, because it's a compression force, we're going to call it typically a strut. You'll often find it referred to as a strut or a column if it's actually in axial compression. Now, you may also have a similar structure. Again, same structure as before, but on the same longitudinal axis because it's the same structure. And if we had a tensile force, okay, instead of a compression force, okay, so tensile force, this is tending to want to pull or stretch this structural member, that would be referred to as a tie. So we've got struts and we've got ties, both of which are axially loaded members and are not beams. Then the other one that springs to mind, which we might think of, is so not that or that, and not the following. Okay, I think I've mentioned it already, but a shaft, right? So if I have again, let's imagine a tube or a cylinder of some description, and we again have the longitudinal axis, just as before. If that structure experiences a torque, which we can refer to or represent rather as a double-headed arrow, okay, torque T, that would again be referred to as a shaft, okay? So you may have, depending on what part of the world you're living in, you may have a different term for that, but loosely that could be termed a shaft because it experiences a torque or transmits a torque. So we've got struts and ties, which are axially loaded. We've got shafts, which are subjected to torques, but what we're focused on, what we're interested in, are these guys up here, beams. That's a structure that experiences a component of loading perpendicular to the longitudinal axis. Okay, so that's the first thing dealt with. I mean, it's fairly straightforward. There's nothing too hectic going on in there. The other thing, before we move on to talk about 2D or planar structures, we just want to also mention that we may have a frame structure. So at the very end of this module, we're going to go on to talk about frames, and we may have we'll apply what we've learned to frames. So a frame structure may also be classified as a beam. May also be classified as a beam, or part of it may be classified as a beam. And again, that's due to the nature of the loading. So let's just flesh that out a little bit. Let's imagine we have a frame structure, and if you studied structural analysis and you've been coming across this sort of stuff in your lectures, your chances are you'll have drawn structures, or you'll have looked at structures like this. Okay, so you got some sort of a two sort of vertical members joined by a horizontal member, the classic simple frame structure. Again, we've got a pin on one side and a roller on the other. Now, if I was to draw a point load, let's call it, or a concentrated load, let's call it P, and let's just, for completeness, specify where P is. It's halfway across the top of the member. Let's call that L over 2 and call that L over 2. Well, if we look at that, the thing that I tend to do with a structure like this, first of all, is I break it up with the joints. That's the easiest thing to do. So if I broke it up, I'd have something like this. And then I could consider what the effect of that loading P is on the various different elements of the structure. So we have P here, that would mean we'd have P over 2 here and P over 2 here. So again, we're considering what's going on at the joints. There'd be an equal, let's just for clarity draw the vertical member right below. So there would be an equal in magnitude, opposite in direction force called P over 2 there and P over 2 there. And again, just for completeness, let's draw some reactions. That would be P over 2 and that would be P over 2. Now, let's think about this. This component, okay, the horizontal component, is a beam, right? Because it's got a component of loading perpendicular to its longitudinal axis. However, the two vertical members are struts because they're experiencing an axial compression. Okay, so that's a strut and that's a strut. All right then. So we've got a frame structure, but when we dig a little bit deeper and look at the components or the elements of that structure, one of them turns out to be a beam, as we have defined a beam, and two of them are struts. Now, we could take that idea a little bit further and imagine that we had a structure which they say the exact same structure, but watch how a change in the nature of the loading changes how we classify the elements. So now let's say we had a force P and it was inclined at some angle theta, which we don't even need to draw on. But let's say it has, because it's inclined, it has a vertical component, let's call that PV, and it has a horizontal component. I'm drawing that horizontal component raised up off of the member just for clarity, but it would be in line with the horizontal member there, in line with its longitudinal axis. So that's going to be PH. Now, if I think about that, breaking that structure up, what do I have? And I'm going to leave off the inclined force, the resultant, and just draw on its components because they have exactly the same effect. So that's going to be PV. That there is going to be PH, horizontal. We're going to have a vertical component there, a vertical component there, or not component rather, but a vertical structural member. So we're going to have horizontal reaction. We're going to have, let's imagine the force was in the center. PV and PH were applied halfway along that horizontal member. Well, that would be PV over 2. That would be PV over 2. And again, we'd have the equal magnitude, opposite direction, being PV over 2 and PV over 2. That deals with the horizontal, or rather the vertical. Now thinking about the horizontal, what have we got? We have that is going to be PH over 2. We're going to have the same thing. So PH is being distributed or being resisted equally by the two vertical members. So we've got PH over 2 and equal magnitude, opposite direction, being applied to the other side of the joint. And that's going to be PH over 2. PH over 2. Okay, so now let's see, we've got a vertical component. We have a vertical component, so that's going to be a beam. And now we have the two vertical members of the structure are also beams because they experience, not only do they experience axial, let's draw some reactions on here, but they also experience a, let me see, they experience a vertical and they also experience a horizontal component, or a component perpendicular to their longitudinal axis. So that means that that also is a beam. And that there is a beam. Now, have I made a mistake? Remember, we have a roller support here, so no horizontal reaction can be generated here. Okay, and what that means is that there is no pH on this side. It means that pH, if pH is pushing that way, we're going to have pH being resisted here This is a roller, so there is no reaction there. We'll draw a 0 through that to indicate no reaction, which means that we don't have a pH there, because we have to have equilibrium of each element, each sub-portion of the structure, as well as having equilibrium of the structure as a whole. So because this is a roller support, no reaction can be generated. It means that there can be no horizontal component of force on the top of that strut, which means there can be no horizontal component of force on the opposite side of the joint, which means that this must be pH. So we got pH externally applied here, being transmitted through this joint, pH, and being transmitted back down to the support at pH. Okay, so that's essentially what we're talking about. It's a really kind of long-winded way of basically saying to you that the definition of a beam, you got to think about how it applies not just to the structure when you're dealing with a single beam on its own, but if we have a frame structure, we have to also think about how the definition applies to the various components within that frame. Okay, so the last condition which we wanted to specify, not even the last, it's only the second condition. So the second condition was that our structure, the structure is 2D or planar. Okay, so what does that mean? That essentially means, I'm not going to write it all out, it essentially means that all the forces, or the actions, action is another term used for force, okay, so all of the forces or actions, they lie in the plane of the page, okay, so let's just first of all say, I'll write down the second condition, structures are 2D or planar, alright, now, okay, that's condition number 2. And what that, the first thing to say is all the forces or actions lie in the plane of the page. So they can all be fully represented or fully drawn onto the 2D page. That also means that all deflections and deformations lie in the plane of the page. It means that the structure can be fully represented in the plane of the page, or the screen, as the case is here. So another way of thinking about that is, if we imagine the page that you're writing your notes on, or the screen that you're looking at, if you imagine that as a two-dimensional flat plane, okay, that plane would be a plane of symmetry for your structure. So the structure is, if you like, symmetrical about the front of the page and the back of the page. So that's essentially I guess, well, it's clear in my mind. Hopefully it's clear in your mind. But I think it would help if we think about some examples. So if we think about a roof truss, for example, the truss in a roof, you might have something that looks like this. And maybe, what else would it look like? You may have that coming down there and that coming down there, and there might be a bar across the bottom, and perhaps you might have a vertical element in the middle, something like this. This roof truss is a planar structure, okay, because any forces I draw on it, okay, can be drawn and represented in the plane of the page. The reactions can be represented in the plane of the page, and any deflections of that structure will be represented in the plane of the page. So there's no deflection into or out of the page. Now that's as opposed to a three-dimensional structural frame. Some sort of three-dimensional truss or structural frame couldn't be represented fully on a 2D page, and so it wouldn't be a 2D planar structure. So that is the second if you like, condition that will apply to our discussion. And then the final condition is that our structure must be statically determinate. Okay, so our structure must be statically determinate. All right then. So what does that mean? It essentially means no more than, let's draw a line under that there, no more than 3 reactions for a planar structure. So no more than 3 reactions for a planar, remember that just means 2D, a planar structure. All right then. So all that means is that the structure can be analysed and the equations, or rather the reactions, can be determined using the three equations of equilibrium. Okay, so what we're saying is the structure can be solved using, when I say solved, all I mean is we can determine the reactions, and once we have the reactions we can start analysing bending moments and shear forces. The structure can be solved using equations of equilibrium. Equations of equilibrium. Alright then. So let's imagine a Cartesian coordinate system. So we have, let's say, an x coordinate, a y coordinate. The x and y coordinates are defining the plane of the structure. Okay. The coordinate direction that is out of the plane, okay, is going to be the z. Right. Z. Now, what we're saying here is, for our 2D planar structure in the xy plane, the sum of the forces in the x direction must equal 0 for the structure to be in a state of static equilibrium. The sum of the forces in the y direction must equal 0 for the structure to be in a state of static equilibrium. And bending moments that apply to our plane in the xy plane, our structure rather in the xy plane, those are bending moments about the z-axis. So the sum of moments about the z-axis must equal 0. Okay, so let's have a little pause here and think about this. If I have a planar structure, and the plane that the structure sits in is the xy plane, well then the moments that get applied to that structure that I'm concerned with in my analysis are going to be moments about the z-axis, and the z-axis is out of the plane. So if I analyse those three equations for my structure, if it's statically determinate, I can solve for the three unknown reactions. Okay, so again, a fairly straightforward idea. Let's just throw down an example. Let's imagine again, basic structure. We have a pin support on the left, we put a roller on the right, and what do we have? Let's say we have a force P coming on here, doesn't matter where it is. We have a vertical, let's call this A, let's call this B. We're going to have a vertical at A. Due to the inclined nature of the load P, we're going to have a horizontal reaction induced at A. Let's call that HA. And because it's a roller on the right hand side, we cannot generate a horizontal reaction on a roller. We're going to have a vertical at B. Okay, so we got one, whoops. We got 1, we got 2, we got 3, we've 3 reactions. Okay, 1, 2, 3 equations, and therefore the structure is statically determinate. Okay, therefore statically determinate. Okay, good stuff. So now, just to demonstrate the statically indeterminate structure, let's imagine same structure, okay, but at A, let's add an extra restraint. Let's add a moment restraint, okay. So if we added a moment restraint to joint A, or to support A, we would essentially have what is called a fixed or an encased or an encastra support, okay. And as such a support, also sometimes referred to as a cantilever support, at such a support we would generate a vertical reaction. Let's try our load P on. A vertical reaction VA. We generate a horizontal reaction HA. Because of the built-in nature of that support, we are also going to generate a moment reaction MA. Now, if we had a roller on the right-hand side at B, we could generate a horizontal reaction at B, or not a horizontal, rather a vertical reaction at B, called VB. Now we have 1, 2, 3, 4 reactions. Okay, 4 reactions. Okay, therefore the structure is statically indeterminate to 4 minus the 3 equations, which equals 1 degree. So it's statically indeterminate to 1 degree. This is a very brief overview of statical determinacy, but for the purposes of this module, that's kind of all we need to know. Okay. So those are the 3 things that will apply and will be true throughout our discussion of bending moments and shear forces. So once those are clear in your mind, what we'll move on to do is talk very briefly, and again, it should be a refresher for you more than anything else, but we'll talk briefly about how do I use those equations of equilibrium to calculate the potentially three reaction forces, because that's the first step we need to complete before we can go on and look at determining bending moments and shear forces. Okay,